Internal structure often overlap in X-ray, reducing the likelihood of finding any abnormalities. As a result, the patient may be given an incorrect diagnosis of SAPHO as a result of having to undergo several scans, which is unavoidable if their condition persists and the radiologists are unable to locate a trigger. CT scan exposes the child to radiation, and overuse of CT scanning has received attention from organizations that regulate medical radiation exposure. Although no side effects have been linked to radiation exposure for CT imaging, the Food and Drug Administration had issued guidance to physicians regarding levels of radiation during pediatric CT examination. Furthermore, the images from CT examination are called slices because they are acquired in a very small, millimeter-sized section of the body. The image slices are displayed on a computer monitor for viewing or printed as a film.
CT works to acquire the necessary data from a specific cross-section or slices that is being scanned. We will now look at it with a mathematical perspective. In this research, we will represent CT scans using a field of linear algebra, specifically the system of linear equation. We will build a system of linear equation using arbitrary data obtained from sending and detecting X-ray beams at a patient's cross-section in the analysis. Then, by using the Gaussian elimination process, we will try to solve it to get the roots or solution values that represent the substances in the slice. We must consider a single cross-section of the brain and divide it in a grid as shown. Solving the cases with this method, we can show that the field of linear algebra can be used to acquire the necessary data to identify the objects being scanned by CT. Given that grid cell A weakens beam by A units, grid cell B weakens beam by B units, and grid cell C weakens the beam by C units as shown in the arbitrary CT report. B1 weakened by 0.7 units as it is passes through grid cells of A and B. B2 is weakened by 0.55 units as it passes through the grid cell of A and C, whereas B3 is weakened by 0.75 units and it passes through grids cell B and C. Using the above data, a system of linear equation can be obtained as shown below, which is A plus B equals to 0.7, A plus C equals to 0.55, and B plus C will be 0.75.
First of all, we should make a metric form of equation in a combined system, which is metric 110, 101, 011 times with metric ABC equals to metric 0.70, 0.55, 0.75, which is in a form of AX equals to B, where A equals to 110, 101, 011, X equals to ABC, B equals to 0.70, 0.55, 0.75. First, we acquire the augmented metric that we require to apply the method of the solution to the sum, which is as 110, 0.70 as a row 1, 101, 0.55 as a row 2, 011, 0.75 as a row 3. Now, we must acquire the REF using Gauss elimination. Firstly, we interchange the row 2 and row 3 of the metric. Then we have 110, 0.70, 011, 0.75, 101, 0.55. Next, we subtract row 1 from row 3 for a new row 3 of the metric, which is 110, 0.70, 011, 0.75, 0 negative 1, 1 negative 0.15. Next, we multiply row 3 with negative 1 for new row 3 of the metric, which is 110, 0.70, 011, 0.75, 1, negative 1, 0.15. Next, we subtract row 2 from row 3 for new row 3 of the metric, which is 110, 070, 011, 0.75, 0, negative 2, negative 0.60. Next, half row 3 and multiply it with negative 1 over 2 for new row 3 of the matrix, which is 110, 0.70, 011, 0.75, 001, 0.30. We finally acquire the REF of the original matrix, which is 110, 011, 001 times with ABC equals to 0.70, 0.75, 0.30. Finally, we reform the individual equation from newly acquired AX equals to B, which is A plus B equals to 0.70, B plus C equals to 0.75, C equals to 0.30. The values of the variable that represent an individual grid cell as stated originally can now be used in the reference to the table 1 to identify the type of the object that is allocated in the grid cells. By using the data in the table we have, grid cell A contains of healthy tissues, grid cell B contains of bone structure, grid cell C contains of tumorous tissues.
In this project, we describe the system of linear equation and how solving them given different type of solution. Then we talk about how CT work, how the scan takes a data that we can use the data to form a system of linear equations. Next, we make use of arbitrary CT cases where a patient is scanned and we have acquired the scan data. Then we acquire a system linear equation. Solve it using one or all the solutions method, and lastly cross-reference the acquired solution value with a collected table given to identify whether those values represent bones, healthy or tumorous tissue. In conclusion, we was able to show what we wanted to, that is using a system of linear equation acquired from the CT data to find and identify the objects present in a slice. Thank you from our group.